just a couple of words about the metric system. The metric system is sort of similar to our place value number system, where we have multiples of 10, and the position of a digit tells you its value, and each position is 10 times the previous one, or going this way, it's 1/10. So 1/10 of this, 1/10 of 1,000 is this, 1/10 of 100 is this, 1/10 of 1 is this, and you keep going. You have negative exponents, that means you have smaller numbers. And you can change from, in the metric system, you can change from one unit to the other. I'm not going to spend too much time on this, but you can use this to measure anything, distance in meters or kilometers or megameters or gigameters or terameters, or grams. You have milligrams, micrograms, nanograms, or picograms. And there's a easy way to remember, at least the ones over here in the center, the ones I had in the previous slide. These ones here. You remember King Henry died drinking chocolate milk. So these are the names, prefixes for the metric system. So some of these are not used very much, like hectodeca, but most of the other ones are used somewhere along the line. So when you measure things in the metric system, you have a prefix. For example, the prefix for 10 to the minus 6 is micro. The prefix for 10 to the minus 9 is nano. These are the most popular ones. Kilo for 10 cubed. These are for big numbers and small numbers. 10 to the 9th is giga. 10 to the 12th is tera. 10 to the 15th is peta. And this words for every one of them, you can see over here. And they can be used for anything, to measure distances, to measure speed, hertz, to measure volume, liters, etc. Now, also just a reminder of how units work. If you take two numbers and you divide, say, one by the other, what you get has units. So you divide 10 meters by 2 seconds, you get 5 meters per second. Also, we have a bunch of relationships, like 12 inches and 1 foot, and which means if you take 12 inches and divide it by 1 foot, make a fraction out of that, then basically this is 1, because the numerator and denominator are the same. 12 inches equals 1 foot, so 12 inches divided by 1 foot is 1. So keep that in mind when you're doing conversions. Okay, we're going to do that in a second, but we're going to look at a force in nature. One of the forces in nature we're going to look at is the electrostatic force. It's given by this equation. You don't have to remember it right now. We're going to do that next week. And it's very similar to the gravitational force. They both have a constant involved. This constant is very small, which means the force of gravity is very small. This constant is kind of large. Okay, but Q1 is what Q2 is. No, let's not worry about that now. It's sort of similar to M1 and M2. So conversions. First of all, I'd like to just review that. As I mentioned before, if you take any number and multiply by 1, you still get that number. And that 1 is the relationship between things you want to convert. For example, let's say you want to convert 7.43 meters to nanometers. Well, you have to know what the relationship between meters and nanometers. Here's the relationship. 10 to the 9th nanometers equals 1 meter. This is one of the things we just covered. So if I multiply this by this fraction over here, that means I'm multiplying by 1. So whatever I get here, by multiplying this out, I will get, it will equal to whatever I started with here, because I'm multiplying by 1. you notice what happens to the units. The meters cancel off, and therefore what's left is 7.43 times 10 to the 9 nanometers. So we've done, basically without knowing it, we've done the conversion, 7.43 meters to nanometers, and it turns out to be 7.3 times 10 to the 9 nanometers. So this is how you do conversions. We're going to do a couple examples here. Yeah, say you want to convert dollars to quarters. We need a conversion factor. I'm choosing an easy one on purpose. We know that $1 is 4 quarters. This is the conversion factor. So we know that if we form a fraction of $1 over 4 quarters, this is 1. Or we can do it the other way around. This is also 1. So when you want to convert, let's say, right, each of these is 1. Let's say we want to convert $25. How many quarters would that be? Well, what we do is we put down the unit we don't want over here, so it will cancel off. So we're going to use this one here, because if we use this one, dollars won't cancel off. You get dollars squared over quarters. So we're going to use this one. And now what happens now is that the dollars cancel off. So we multiply 25 times 4, which is 100, and we get 100 quarters will give you $25. Okay. So I know these are pretty easy, and I chose the first couple examples to be quite easy. Let's look at a little harder examples. For example, you really see what I look like, but you haven't seen me stand up. I'm not too tall. I'm 5.5 feet tall. How many inches is that? Well, I must know the connection between inches and feet. Okay, so I start out with 5.5 feet, and I'm going to multiply by the conversion factor. That means this, where I can put one of these on the bottom, one of these on top. Which one do I put on the bottom? The one I want to cancel. Which one I put on top? The one I don't want to cancel. So you notice that the feet cancel, and the answer is 12. 66. So I'm 66 inches tall. Same thing here. If you want to convert centimeters to inches or inches to centimeters, you got to know the relationship between them. So let's say 200 inches. How many centimeters is that? So again, you're going to form a fraction here. You're going to put the centimeters on top because you want the inches to cancel, the inches on the bottom. And lo and behold, you get 50.8 centimeters. Okay. I know these are easy. We're going to go to some harder ones. So let's say this desk, the desk I'm sitting at, is a certain number of meters. And we want to change that to kilometers, which is very easy. But also we want to change that to astronomical units. 1 astronomical unit is 1.5 times 10 to the 8 kilometers. So first of all, let's take the size of my desk, and well, we can make a fraction out of this. We can say 1 kilometer, right? Or we could say the other way around. The whole point is that first we need to make, first we need to get a number and convert it to kilometers. Now let me see, I think I should have, let me check my numbers here. So if you have, let's say, let me make up a number. For some reason, I don't have a number here. So I need to have my desk. First of all, I have to measure it in meters. Let's say it is 0.78 meters. Since I'm going to be using this conversion, I have to change this to kilometers. So basically, I have to multiply it by, I want to change the kilometers, so I'm going to put the kilometers on top and meters on the bottom. This is meters. So I'm going to multiply by this. So now the meters will cancel, and I'll have this in kilometers. And then I have to multiply it by this conversion. So the kilometers would be in the bottom. And astronomical units are on top. Okay, so let's just look, when we do this multiplication, let's look at the units, how they, I'll do it in blue. So the meters cancel here, the kilometers cancel here. And when I do all this multiplication, I will come up with a number. We're not going to do it here. A very tiny number, obviously, that will express the width of my desk in astronomical units. It's going to be very tiny, obviously. It's not too big. But let's do a double conversion where we want to convert 1 week to hours. Okay, so we'll start off with 1 week, like I have over here. And we know, I mean, we're going to have to do a couple of conversions because I don't know how many hours there are in a week, but I do know how many hours there are in a day, and I know how many days are in a week. So we're going to do those multiplications here. 7 days are in a week, and 24 hours in a day. Everybody knows that, right? And so what happens to the units here? This cancels that, this cancels that. And so the number you get here is hours. Also, we can, let's say we want to do another conversion here. It converts 1 year to seconds. Okay, how many seconds are in a year? So again, we don't know how many seconds in a year, but we can figure it out because we know how many seconds in a minute, how many minutes in an hour, how many hours in a week, how many hours in a day, how many hours in a day, and how many days in a year. So multiply all these things together. Okay. Don't forget there's a multiplication sign here. This 1 year equals this times that times that times that. And if you do that, you get 3.15 times 10 to the 7 seconds per year. So here's a couple of interesting ones. Well, I think I'm going to skip these already. These are similar, but I'd like to do one other conversion here for you. Cover this up. So let's say we want to convert 100 kilometers a speed. Somebody's driving how many kilometers per hour? How much would that be in meters per second? So we start off with 100. You saw a little bit of the answer here. We start off with 100 kilometers per hour. All right, so we're going to change it to meters per second. So first of all, we're going to put the relationship between kilometers and meters. Right? We know that 1,000 meters is 1 kilometer. And we want the kilometers to cancel because we want eventually to be in meters. Now we want to change the hours to seconds there. So we know that 1 hour is 60 minutes. So the hour will cancel. And 1 minute, 60 seconds. So let's see how these units work out. So kilometers cancels kilometers, hours cancels hours, minutes cancels minutes, and we have left meters on top and seconds on the bottom. So basically multiplying all this out, you get 27.8 meters per second. Okay, so I want to do one more example. 60 miles per hour is equal to how many feet per second? So basically, miles per hour is usually what you see in a car, but if you're running or walking, basically your speed may be feet per second. It'd be more convenient unit. So let's start off with this. Now this is going to be your first, I'm going to help you out with this. I'm going to just get you started. Miles per hour, that's the first unit here. And we want to wind up eventually in feet per second. And we don't know directly how to do this, but we do know how many seconds are in an hour. And we know how many feet are in a mile. 5,000, if you forgot, 5,280 feet are in a mile. So let's see if you can now use this information to see which is the right answer here. I'm going to take a minute for you guys to work on this so you get used to the idea that you are doing stuff as we go along, because you're applying what we just learned. You can change the hours to minutes and minutes to seconds if you want, or you may know that 3,600 seconds are in an hour. Oh, the other way around, sorry. 3,600 seconds or 1 hour. And that 5,200 feet are a mile. Okay, so I'm going to sort of sneak a peek at what you guys are doing, how you're doing. Yeah, I sort of like to have that on the side here. So the people answered, yes, you guys are right, 88 feet per second. Okay. Marie, what did you say? Could you post that on Blackboard? What were you talking about?
Hi, Professor. Sorry, I was asking about the list of metric, the one, what you have.
Oh, that one? I
Yes.
think it is there.
Okay,
I
I'll look for it.
think it is there already. Okay. So we're now going to move on to another topic, and that's going to be trigonometry. Okay. First of all, we know that angles are measured in two types of units. Well, degrees is one of them. A full circle has 360 degrees. And we're going to look at another way to measure angles, and that's going to be radians, like over here. But first of all, you may be interested in thinking about who came up with 360? that one revolution is 360 degrees. Well, where did that come from? Well, we think that basically in ancient Greece, they used, first of all, there's a couple of things about the number 360. There are 360 days in 1 year about. So this came about in ancient Greece, as measurement systems. And also, there's a numbering system. We saw that we had a base 10 numbering system, but there's a numbering system, a system to count, called using a base 60. So this could be possible why they use these 60s but there's nothing special about it. You divide up the circle into 360s. But what we're going to do is we're going to look at something else. A radian. What's a radian? Let's say you have an angle here. This is a circle whose radius is r, so this is r and this is r. And let's say this distance, this arc length, is also r. All three of these are r. So by definition, this is 1 radian. This is how a radian is defined. Okay? It's that part of a circle where this is equal to the radius of the circle. The arc length equals the radius, and therefore theta, the angle, is equal to 1 radian. Now, how many, therefore, of these radians would be in a circle? Well, you know already that it's 2 pi radians, or approximately 6.28 radians to span the circumference of a circle. Let me just show you this here. So here it shows you that to go half a circle, this is a radian, it's another radian, it's another radian. It's a little bit more than 1 radian, than 3 radians. How much more? 0.34. So, okay, so 3.34, 3.14 radians in half a circle. If you double this, like I'm going to do over here, if you double that, you'll find out that it's 0.28. 6 and a little bit more, 0.28 radians in a full circle. So in this case, 2 pi radians equals 360 degrees. So if I go around like this, come back to the same point, I've rotated 2 pi radians, 360 degrees. Pi radians would be, say, rotated from here to here. Okay, that's pi radians, that angle. From here to here is pi over 2. From here to here is 3/4 pi. Okay, et cetera, et cetera. So in this case, pi over 4, pi over 2 equals 90 degrees, pi over 4 equals 45 degrees. So how do you convert between these two angles? Well, converting degrees to radians, this is the formula used. There are, let's say you want to convert 30 degrees to radians. How many radians would that be? This is a conversion. The degrees divided by 180 times pi. And if you do that, you'll find out that 30 degrees is 1/6 pi. How about converting the other way? Well, the other way is converting from radians to degrees. Radians over pi times 180 equals the degrees. So for example, let's say we want to know 2/3 pi. How many degrees would that be? 2/3 pi. Well, put it in here. Of course, you notice that the pi's will cancel. You got a pi in the numerator, pi in the denominator. So it's 2/3 times 180. So 2/3 pi equals 120 degrees. It's supposed to be an equal sign here. I think okay, we're going to come back to this. So, so basically any angle and I'm going to right now concentrate on some popular angles. Any angle can be written in terms of degrees or some kind of pi radians. So for example, I'm going to show you this in a minute. This angle here is 0, yes. This angle is 30 degrees, but it's also pi over 6. This angle is 45 degrees, it's pi over 4. This angle is 60 degrees, it's pi over 3. This angle is 90 degrees, it's pi over 2. Now we could keep going, 120 degrees. These are all multiples of same ones you have here. Okay, we're just going the other way. And then you could keep going over here, keep going all the way around. And each of these is, you get these numbers here by using that formula that we had in the previous. So I'd like to now go for a minute to another application. And show you a couple of things. Oh, I forgot, I should do one other thing before I do that. Okay. So let's see, we can convert, using the formulas, we can convert 4/3 pi into degrees. All right. These are all other ones. Let's just do one. Let's see. Try to convert 4/3 pi into degrees. Don't forget the formula is kind of big here for all these conversions. So radians. Don't forget we got 4/3 pi radians. So you're going to put 4/3 pi up here. Now this pi is going to cancel this pi. So you got 4/3 times 180. How much is that? A little bit more than 180, right? 240. All right. Let's do one more. Again, you guys can do one more. Do this one here. So don't forget, you're going to put in the formula. This is 5/2 pi. So 5/2 pi divided by pi times 180 gives you, so you guys are doing here. So it'll be the pi's canceled, it'll be 5/2 times 180. So here, we're not going to do these too much, but here's some more. On the video, you can practice more, if you watch the video, to do these conversions the other way. So this is exactly the same, but the other way. I'm going to give you the answers here in the next slide. Okay. Okay. So So we're going to go, this is called the unit circle, which I started doing before. So we're going to look at the unit circle. It's basically what's a unit circle. It's a circle where you can, you can change the angle over here. The radius of the circle is 1. So the distance is 1. If I rotate it, say to this spot, okay, this is what you're looking for here is a right triangle. This is 1. These are different numbers over here. Okay, so we have the radius, which is 1. That's why it's called the unit circle, because the radius is 1. Get the pen up here. Okay, but this is some number, and this is some other number, and this would be some angle here. Okay, that'll be the same as over here. I'm just redrawing this little triangle over here on this side. This side here is opposite this angle. This side here, x, is adjacent this angle, and r is the radius. The three things are related by Pythagorean theorem here, that r squared equals x squared plus y squared. And again, these are numbers here. You can see, you can measure what the numbers are. Okay, if this is 1, you can actually measure it, and we're going to measure it in a bit. But we're going to define a couple of functions here. So for example, we have the hypotenuse, which is r, will always be the radius of the circle, and the other ones are called legs. We're going to define a couple of terms here. Again, this is called the hypotenuse. If this is the angle theta, that this is opposite that angle, and this side x is adjacent to that angle. And there's going to be a couple of trigonometric identities that you've encountered. The sine of theta is the number that you get by taking this length, the opposite the angle, and dividing it by the hypotenuse. The cosine of theta is taking the adjacent leg and dividing by the hypotenuse. And the tangent of theta is taking the opposite leg and dividing it by the adjacent leg. So now I'm going to go to the unit circle demonstration that I had before. All right, so this is that unit circle that we've been talking about. And I can choose to show, as I go around here, you notice two things happen. As I go around here, this gets bigger and this gets smaller. Now the cosine of this angle here, first of all, I'm going to show you the grids here. So don't forget the radius here is 1. Okay, so each of these boxes is 1/2, since the radius is 1. So if I go around, this decreases, this side increases. These are the coordinates right now over here. You can see the coordinates of that grid. So, and the angle, and this is the cosine. Don't forget, the cosine is going to be adjacent over hypotenuse. This is x, where the x is before. Now, don't forget, the x is 1 now, so right over here, 0 degrees, cosine is going to be 1, so it's x over 1. Don't forget the hypotenuse is 1. And as we go up, that blue leg gets smaller and smaller. Therefore, the cosine gets smaller and smaller. You can see it gets smaller and smaller here. And once you get into here, that blue arrow is negative. So that's why cosine is negative. So one of the things that you'll notice that every point along the circle has x and y coordinates, and the cosine is in fact, for the unit circle, the cosine is in fact equal to the x coordinate. Right now, the x coordinate is 0.899, cosine is 0.899, and this angle will be 26 degrees. Okay, I can do the same thing for sine. So right now, the sine is opposite over adjacent. In other words, it's the green arrow divided by the hypotenuse. So the green arrow right now is 0. The green arrow is 0. And therefore, the sine starts at 0. And if I go up like this, the green arrow gets bigger, 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 bigger. It's the biggest over here. And then it starts getting smaller, smaller, smaller. The green arrow is the sign of the angle. Whatever angle I have, that's the green arrow. Okay. Now you can do the whole thing in radians. I'm just going to leave it over here. Now there are special angles that we're going to concentrate on. I'll just finish this up in a couple of minutes, and then we'll begin with this next time. There's not much more here. These angles are special. Why are they special? Well, let's start over here. So right now, we're going to look at cosine. Cosine is equal to 1 right here. And it's because the blue arrow is equal to 1, and the hypotenuse is equal to 1. So they're both the same. X is equal to 1, and the hypotenuse is equal to 1, and therefore the angle is 0 degrees. I'm going to go up to the next one here. This angle is going to be 30 degrees. The special angles are 30, 45, 60, and 90. Now, this angle, 30 degrees, it turns out that for these special angles, you don't have to express where they are along here, the coordinates with decimal numbers. You can actually express them with fractions. And I'll show you this next time. But anyway, right now we'll just look at it. 60 degrees, the coordinates at 60 degrees are this. At 45 degrees, the coordinates are this. They're the same. It's 45 degrees. That's why cosine is 1. Cosine is the square root of 2 over 2, I'm sorry. And if we go up further, 60 degrees, again, you're going to get, why are these such nice round numbers? So, okay, we're going to do that next time. We're going to pick up right here next time. But let me just finish this off. And if you go over here, right, the cosine is 0, so therefore the x coordinate is 0, therefore the x will be equal to 0 since x is 0. And as we go further on to the next one, the whole thing repeats itself, except for sine. Okay. So I am going to stop recording.